Welcome back. Earth's interior. Wait a minute, didn't we talk about this? The inner core, the outer core, the mantle, crust, all that business? Didn't we talk about that? Yes, we did. But how do we know what's inside the Earth? I just told you that. Did you take it for granted? You believe me? You believe this crazy person? Well, yeah, it's okay if you don't. But let's investigate a little bit. So how do we know what's inside the Earth? We cannot directly study the Earth's interior. I don't care what you saw in a movie. We can't go to the middle of the Earth. Hell, we can't even get through the crust to the mantle with any type of machinery that we have. Drilling, vehicles, whatever. We can't do that. It gets too hot. So we had to use remote sensing, which is a technique widely used in geology and a number of different things, construction. So we had to have some way of figuring out what's in there, but not being able to look. We can't see. So we had to use remote sensing. So we have to use those seismic waves. Seismic waves and how they travel through the Earth is one of the best methods available to analyze the Earth's interior. Remember what I was talking about with P waves and S waves? And P waves, they travel through both solid and liquid, where S waves only travel through the solid portions of the Earth. Well, that's kind of what helped us figure what's inside the Earth. Now, as waves travel through a medium, they kind of are bent, called refracted. It's, again, the sheer physics of things. And when they go from one medium to the next, they're extra bent. But in any case, so for example, there was an earthquake in Kobe, Japan in 1995. Just an example, right? Waves travel through the Earth, so P waves and S waves. The red is the S wave, and the black is the P wave. So you'll see all of these waves emanating from the focus of the earthquake, kind of all peeling off. But when they get to the outer core, which is liquid, those red arrows stop. In fact, they're just deflected off. They just kind of bounce off. They're not shown doing that in all cases, but they just bounce off. They can't travel through liquid. However, with the P waves, they can travel through not only solid, which mantle's mostly solid, but also the liquid outer core, back through the solid inner core, back through the liquid outer core, back through the mostly solid mantle. So on the opposite side of the Earth, we can detect P waves, but we can't detect any S waves. Therefore, if we know the physics of these two waves, one can travel through liquid, one can't, and we don't detect the ones that can't travel through liquid on the other side, there must be liquid in the middle. Bing, bang, boom, done. Now, how they're kind of bent and refracted or deflected, again, that goes back to a little bit more of the physics of it, but you can analyze that to see how they're bent, refracted, deflected. You can analyze all that stuff. It's crazy. It's physics. Check it out. So again, S waves are reflected out the outer core or bounce off, deflected, so they can't travel to the other side of the Earth. Again, the reason why is just the sheer physics of S waves. That shear wave, it just can't travel through liquid. Whereas a P wave, compressional wave, can. I don't know. There you go. Actually, I do know because I studied physics. But too much here. Too much for here. But just in general, again, yeah, we just use those body waves, and that helped us figure it out. We can detect P waves on the other side of the Earth. Oh, okay. There must be, but not S waves. Okay. There's liquid in there. Boom. There's other ways to see the below of the surface as well. For example, we can wait for samples of what's inside the Earth to come up. So magma is what we call liquid molten rock underneath or below the crust, kind of between the mantle and the crust. So bits of the mantle will melt because the mantle is mostly solid. But under certain conditions, mantle material will melt in certain places, becoming less dense, pushing its way up through the crust. Magma becomes lava once it gets at or near the surface. So in essence, it's bringing up that stuff from the mantle up to the surface. So we can wait. In fact, that's how diamonds get to the surface. Diamonds were made billions of years ago in a type of volcanic environment that no longer exists, and those diamonds were created in the depths of the crust and the mantle, but brought up to the surface. So therefore, there's maybe some diamonds floating around in the mantle. So we can wait for the stuff to come up, or go to places where there's been eruptions, or we can drill down, retrieving sample by drilling into the Earth's interior. But as mentioned, we can't really drill that far. This ain't, real life is not a movie. I don't know if you saw The Core. Do I have that sitting around here somewhere? The Core, a movie where the Earth's core stopped spinning, which it does. The Earth's core stopped spinning, so they had to drive a machine to the core to explode a nuclear bomb to kickstart the Earth again. Spoiler alert, they do it, but everything about that is just improbable. You can't go down there. People tried. In fact, you know how we have the space race with the Soviet Union kind of in the 50s and 60s, the first to race to the moon? Well, there was another race. The U.S. had with the Soviet Union, now Russia. And that's to see who could drill the deepest. So instead of going up, who could go down the furthest? Well, the Soviet Union, later Russia, won. Hooray for Russia. So, I think we finally gave up after saying, well, why are we doing this? And it was just to see how deep they could go. That was it. So Russia won. They drilled down 7.62 miles, finishing in 1994. That's when they were reverted back to the name Russia after the Soviet Union. And that's the deepest artificial point on Earth. That's the deepest we've ever gone. It's the deepest hole in the world. And, for no other reason than just to see. So there's some science behind it as well. But as they started to drill down deeper, it gets warmer the deeper you go in the Earth, even in the crust. And so even at this depth of 7.62 miles, it became too warm for the metal machinery to work, the special things that they had to build to even drill that far. It just became too warm. The rocks were acting weird when they heat up, and so they just couldn't go any further. So we haven't even drilled to the mantle. We've only drilled through a little bit of the crust. Imagine that. Here's a picture of what it once looked like, the drill area. And it was actually right near the ocean, kind of maybe the thinnest part of continental crust. And so they tried. This is the part where they have the drill. So the way to do it is they would drill down, put another kind of drill pipe on top, drill down, put another pipe on top, drill down, put another pipe on top, drill down. So you keep adding pipe on top to spin the drill at the bottom. So now, what is it? Is it a famous landmark? Is it a famous landmark? Dang it. Is it a national treasure? Nope. It's just a hole in the ground with a cap on it now. So that's it. All right. Oops. Move me a little bit. Yep, that's it. There it is. The Kola super deep borehole. That's what it was worth. I'm guessing that guy helped drill it. There it is. Deepest hole in the world. Doesn't it look better than Disneyland? I think so. In any case. So let's go ahead and pause here. When we come back, let's talk about measuring earthquakes. There's a couple different ways to do it. Something we'll do in class, in lab, for sure. So let's go ahead and pause here. And when we come back, we'll talk about measuring earthquakes. See you back here in just a second.